Fine. Good afternoon to you all. This is the example what we have practiced in the session 1. This is a two-cell straight box girder which contains only the self weight, and we have provided two bearings on either side. Now this session we will complete the other loading part, that is your superimposed dead load or bearing surface and pre-stress load, and plus the construction stage analysis simulations. Fine. So as we are seeing this model which contains our material property, section property, and this is the one we have to create it. I will show it again. Yeah. So the loading part, only self weight is applied for this model. And now, now you can able to see the screen because this is due to the internet problem, I think. Fine. Now the first part, first we have to define the time dependent material property, which comes under the property. This property we are defining because of to perform the construction stage analysis. The first one, creep and shrinkage. Before that, I'm just changing the unit to Newton millimeter. Newton millimeter, so I can change the units at any time. And then the first property is creep and shrinkage. Add. We are following IRC 112. I'm giving the name as C and S, the short name for creep and shrinkage. This is for 40 Newton per mm square. Same 40 grade of concrete. And relative humidity is 70%. And notional size of member, we have to calculate as per the formula, that is H equal to 2 into area, section area divided by perimeter in contact with atmosphere. I'm entering 1000 millimeter, and type of cement is normal cement. Age of concrete at the beginning of shrinkage is 3 days because first 3 days is the liquid stage, so we are calculating your creep and shrinkage effect after 3 days. Show calculation result. This is showing the creep coefficient and the shrinkage strain values. It's added over there. And next property is compressive strength parameters. Compressive strength, add, giving the name. And again, code is selecting ISA 112. This is FCK plus delta F. So I am entering 45 Newton per mm square for a normal cement. So this is a compressive strength variation graph. Click OK. So these two properties we have defined it, and then as you are seeing in the tree menu, these two inputs, the creep and shrinkage and compressive strength parameters, which is showing in blue color. What it means, this functionality is not yet completed. We have defined it, still that entire time dependent property which is not assigned to the model. That is the meaning, which if any command which you are seeing in the works tree in blue color, that means you have defined it but not completely associated with the model file. Now how to connect with this one? Go to material link, select the creep and shrinkage function and compressive strength function, connect with the grade of concrete. Add and close. Now you can see this property is now black color. That means this functionality is completed. Now this grade of concrete I will just change to M40 grade so that we can easily understand it. So this is the model which you prepared earlier. Maybe the number of divisions that the dividend will be different, but remaining things are same. So two such straight box girder. It is 20 meters. Fine. So self-fit is applied. Now other load cases we have to apply one by one. And before that, we should create the group. This group we are creating for constructions analysis purpose. So we have the group is structure group, boundary group, load group, tendon group. The first one, structure group, they have defined the we have created the group name is girder. Now you are seeing is a girder. So how many number of segments you want to simulate in the construction stage analysis? So that many group or that many name we have to define under the structure group. We have created only one group. Select all the members. Just drag and drop. So this 20 nodes and 10 elements are assigned with this group. So what is the purpose of this group definition? Whenever we are performing construction analysis, the individual member or individual load case will not appear in the input table. Instead of that, it will show only the group names. So if any members or any loading parameter which is not assigned with the group, then that information will be omitted while doing analysis. So that's why we are creating groups, and all the information has to be connected with the groups only. And support group, we have created two groups, one is support and links. And then load group, we have created self-weight, cross barrier, pre-stress, and wearing surface. So totally 4 load cases we have defined it. A tendon group is not required, that we will see the result one by one. Now when it comes to the work, from the existing work, I am just assigning the support condition to the proper group function. Right click the support condition, go to table, and this is a group. We have to select by default. It was a default earlier. Now we have to select this. All the support conditions are in the support group. And similar way, right click on the elastic link, go to table, the last corner group name, select the link. So this is the two groups we have defined it, that is support and links. So elastic link and rigid links comes under the link group, and support comes under support group. And then self-weight, right click, go to properties, select the self-weight group, and this is a load case name, this is a load group name, and click modify so that the self-weight is assigned with the self-weight group. Now how to define other load cases? Go to the load, static load cases. Previously we have defined self-weight. The other load case we have to define now. This is our I'm giving a short name. It is my CB, that is the cross barrier. This load type is dead load of component and attachments. And WC is the wearing surface. The load type is dead load of wearing surface and utilities. Add. And then pre-stress, load type is pre-stress, add. So these 4 load cases we have, and the dynamic analysis we will perform separately, and also the moving load we will apply separately. So this is the total 4 load cases, and the remaining load case I will apply one by one. That is, first one is a cross barrier load. It is element type beam load. This is my load case name, that is our cross barrier CB. Load group name, I created the name cross barrier. And from here, the eccentricity previously we have used the center top offset for the section definition. So our reference of the eccentricity, which is followed from offset, we have to select the offset distance from the reference axis. As far as model is concerned, it's a straight bridge, so the local axis and global axis are parallel, it is same. So I'm selecting local axis. Again, the distance I and j, It is referenced from the element location. Before that, I will just show. Go to the work. What is the cross section over here? Now you can see this is a 10 meter. Width is 10 meter. This is the reference picture. B1 is 10 meter I entered. So that means from the center it is 5 meter. So I'm keeping as a 5 meter. Load intensity is minus 2.5 kilonewton. Okay, this is Newton per meter. I'm changing the unit to kilonewton per meter. So now we want to apply minus 2.5 kilonewton per meter and select the member and apply. And then one more time eccentricity is minus 5 for the same loading. Again select the element and apply. Close. Now you're seeing this is the cross barrier. Now you're seeing the load value as well as the eccentricity which is mentioned in the geometry. So this is the cross barrier load which we have applied at both the edge of the slab. And next is bearing surface. As this is a beam model, so we can directly apply the bearing surface load per meter length on the beam element itself. Go to the element. It is bearing surface WC. Bearing surface load group. There is no eccentricity. The load direction is Z direction, that's vertical. The load intensity is minus 1.5 kilonewton, 1.5 kilonewton per meter. Select the member and apply and close. Now you are seeing this right click display. This is my bearing surface load and this is my cross barrier load. So both the loads we have applied it. Our next load case is pre-stress. So how to apply the pre-stress generally? So the application of pre-stress, the first step we have to define the pre-stressed cable profile. Sorry, the pre-stressed cable property, that is comes under the material property. What kind of material it is, that we have to define first. Properties, material, this is the material. Actually this is supposed to be the user defined function because this steel grade and the actual pre-stressed cable is a high tensile wire. That properties are different. So how to use the user defined? You can select the user defined, you can give the values. Otherwise it's a steel property, Indian standard, database. This is the property of the section. Okay, for time being I will select the same property. In actual condition we have to give the actual property of the cable from the manufacturer. I'm giving the name as the steel. Fine. So next go to the load. This is the load case for the temperature and pre-stress application. So this is the pre-stress loading step. The first one is redundant property. Select. Add. So this is the pre-stress redundant property table. Here what are the parameters we are giving? First we are selecting what type of tensioning it is. Either it is a pre-tensioning or post-tensioning or external pre-stress. We have all the three types. We have to select the type of the tensioning first, and then accordingly the remaining parameters will be. And this is the post-tensioning method, so I'm selecting post-tension. And the material, this is the material what we have defined just now. So I'm selecting steel. And then next part is total tendon area. Here the tendon area we have to select by the number of strands and strand diameters. That's a standard procedure. So this icon will take you to the database for the strand diameters. This is my standard strand diameter which is available in the program. And similarly, the number of strands. So in the cable, in the one cable, how many number of strands are there in which diameter that we have to define. So I'm entering 19 number of strands with a 12.7 mm dia strands. So this is my total tendon area and that diameter is 90 millimeter. And relaxation coefficient as per the standard, so I'm selecting IRC 112 2011. This is for normal relaxation. And then ultimate strength, yield strength, curvature friction factor, wobble friction factor is as per the standard. And also this is editable, we can modify the properties also. And also it is considered the anchorage slip is 6 millimeter as per the standard. Give it the name as tendon. So the property is defined now. And next is we have to define the tendon profile. This is the input table for the tendon profile generation. The tendon name, I'm giving the name as a T1, that is tendon 1. We can give any name for that. And the tendon property, the one which we have defined just now, that is tendon property. And element, assigned element, for which element you have to apply. So this is the element number 1 to 10 because this is a single line diagram for box girder. The same way, if it is I girder composite system grid edge model, then we have to define the cable profile for every girder one by one. So in that case, we have to select the particular girder for the precise cable profile generation. And then input type is 3D. We can give the input in X, Y, Z direction, that coordinates, and curve type is a spline. This transfer length is that the straight length of the cable portion at the anchorage location. That is the transfer length. And this is the preview of the section, preview of the cable profile based on the coordinate system over here. And before entering the value here, we can directly make one Excel sheet and then we can copy paste from the Excel sheet itself. So this is the Excel sheet. So this is the cable 1, 2, 3. Let's create the 3 cables. The first cable coordinate is 0, 0, minus 0.5. And let's check what is the depth of the girder over here, which is 2 meter. Fine. So next is 1 meter. So I will calculate the cable coordinate for 10 meters because total length of the girder is 20 meters, so that I can make it symmetric tendon from the center point. This is first cable coordinate. I'm copying for second cable, and this is for third cable. This I am starting from 0.7, 0.9. So this is the cable coordinate which we randomly calculated in the Excel sheet. Now I'm just copy paste this coordinate, only the values. Go to the software, paste it. Here at the bottom we have the option to make symmetric. Make symmetric. This is the profile view. And the profile insertion point is the starting point of your cable. This is starting from element number 1 and apply. Now you are seeing the cable profile which is generated, which you are seeing in the model file. And the same way, change the name to T2, that's the second cable. Put the existing coordinates in the table. Again, copy the second coordinate system from Excel sheet. Paste, make symmetric, apply. Again, change the name to T3. Paste, make symmetric, and apply, and close. Now we are seeing the 3 cable coordinates. We can see the cable profile points. This is the 3 cable which we are seeing at the center web. And the same way we have to create the cable profile at the outer web also. For the simplified process, we can copy these 3 cables all together and paste it at the outer girder also. I'm selecting all the 3 girders. We have to find out the distance, and before that let me see the distance between these two. Y is 2.75. Fine. So it's copy and move. Equal distance, that is 0, 2.75, 0. We are giving the value only in y direction for the currently assigned element. Click OK. Now we are seeing the cable profile and the outer web also. And one more time, equal distance, the distance is 0, minus 2.75, 0, currently assigned element, and click OK. Now we have 6 cable profile in the geometry. Now you can see the cable profile which is on the center web and the outer webs. So 3 webs having the cable profile. Now this is the isometric view, perspective view. We are seeing the cable profile which is assigned in the model. So totally we have 9 cables. Now we can see the total number of cables are 9. And then again go to the loading part. So next is a tendon pre-stress load. Go to tendon pre-stress load. Select the load case name is pre-stress, PS. Load group name is pre-stress. Select all the cables. So if in case practically if we have the stage-wise pre-stress, in that case that many load case and load group we have to define. And here for the example purpose, I assume that all the cables are stressing at the same day. If the time difference in the stressing, then we have to create that many load cases. And the stress type, we can apply the jacking force is the force type or stress type. I'm selecting the force type, stress value, force type. So both in jacking, so I'm selecting both in. Now I can change the unit to ton force, and the ton force at both the end is 240 ton. And this grouting information after one stage. This one stage is the one construction stage. So that means whenever you are activating the pre-stress, and the next stage, next construction stage, we are applying the grouting details. Close. So now you are seeing in the pre-stress load cases display. Now you are seeing the force value in the model. So the processing part is completed now. Next is the moving load. Load, moving load part. Select the standard. Then accordingly this input will enable. So the first one we have to define the traffic line lanes. Traffic line lane. Add. Giving the name as a lane 1. Eccentricity is the distance between the member to the center of the vehicle. So I'm giving the eccentricity value is 2 meter. Wheel spacing will update automatically. So initially it's taking 1.8 for the class A vehicle. Automatically it will update whenever the 70R vehicle is occupied in the lane. And span length is 20 meters, so that the impact factor for the span will be calculated according to the span of the bridge. Or otherwise, if we have manually calculated the impact factor, we can directly feed the impact factor also. And then vehicle load distribution through the lane element. If in case if your structure is a relay system, then we have to select the vehicle load distribution through cross beams. As far this project is concerned, it is just a lane element. And the moving direction, it will check the condition for both the direction, that's for forward direction and backward direction. And the selection by 2 points, we have to select the 2 points. This is my starting point, this is my end point. And click apply. And again, change the name to lane 2. Remove the existing table value. This time eccentricity is minus 2 meter. Remaining parameters are same. Again, I have to select the starting point and end point in the model. One more time. Apply. So totally we have 2 lanes is created. That 2 lane we can see in the geometry right away. So this is the lane 1 and lane 2 which is created. Next is the vehicle. Vehicle, add standard vehicle. These are the standard vehicle as per the IRC standard. So I'm selecting class A vehicle and 70R vehicle. So the 2 vehicle we have selected in the geometry. Next is the moving load cases. So in moving load cases, what we are giving, we are selecting the moving load combinations for that. Add. Giving the name as MVC, that is the moving load combination. We have the condition for we can make the automatic load combination or manual combination. Automatic combination means if we select here, I can add the loading data. This is my class A and 70R vehicle occupied by both the lanes. I can select this way. Otherwise, if we remove the automatic combination, then I have to select that vehicle, which vehicle coming in which lane, that specification specifically we have to mention in the model file. Okay. So I will show the manual modeling. So this is the minimum number of loaded lane is 1. This is for 70R vehicle. This minimum can be 1, maximum can be 1. because every two lane 170 here. Select both the lanes and click OK. We have two conditions manually we have created now. And click OK and close. So we have applied the loads that such as self-weight, cross barrier load, bearing surface load, pre-stress load, and live load. And the one more load case is that is the dynamic loads, that is as per the response vector method. Go to the load, dynamic load. We have two methods, response vector method and time history. We are following the response vector method, so go to the response function, RS function, that is the response vector function. Add, this is the input data. First, we have a data in Excel sheet, you can directly copy paste, otherwise you can go to the design spectrum. This is as per the standard, so we are selecting this code, this is IS 1893 2002. This is updating in the next version. And this is zone wise is zone 4, and soil type is medium soil, damping is 5%, multiplication factor is 1, importance factor is 1, response reduction factor is 3, maximum time period is 6 seconds. And click OK. This is the function which is defined for dynamic condition. And next I have to define the response vector and load cases, RS load case. And here I have to define the condition for X and Y direction. So I'm keeping this is X direction, and excitation angle is 0, and model combination control, we have the method for SRS method, CQC, absolute maximum, and linear method. Subtracting CQC method and apply damping method. You can select damping method by model damping, mass plus stiffness properties, and strain energy properties. And interpolation method for spectral data, it's a logarithmic method, it's a more accurate method as of now. And add. Yeah, spectrum function we have defined it. Yeah, add spectrum function. This you have defined it. Spectrum function as per IS 1893, zone 4, medium soil. We have defined it and click OK. This is the design spectrum. This will appear here. Set the condition, add, the X direction is added, and next is the Y direction. So give the name is Y direction. Now the excitation angle is 90 degree. Remaining parameters are same for the same function. Add one more time for Y direction. It's fine. And next is we have to define the eigenvalue analysis control for dynamic analysis. Go to eigenvalue analysis. So for the eigenvalue analysis, we have type of analysis by eigenvector and ridge vectors. We are selecting by eigenvectors by Langos method. By Langos method, we are giving the number of frequencies. If we give a number of frequencies 15, that means it will generate the number of mode shape is 15. There we are checking your natural frequency of the structure and time period and tolerance value. And mainly we are looking for how much mass is participation in the seismic force. That is our mass participation factor in X and Y direction. It should be more than 90% as per the standard. And click OK. So this is added. So these are the load cases which we have completed. And for the dynamic condition, we have to convert the load to mass. That is, go to the structure type. Here the convert sulfate into masses in all the three directions, X, Y, Z. Click OK. It's added. Now next is the construction stage analysis. So we can access through load, construction stage, define CS, that is a define construction stage. This is a construction stage input table. So here the name is stage 1 I'm giving. Stage 1. Duration of stage 1 is 30 days. And the element, this is the group name which will display here. As I told you earlier, what are the group name we have defined here? That same group name will appear here. Individual load cases or load group will not display here. Only the group name will display here. So this is the girder. When we are placing the girder, or when the girder is taking off its own weight, at that time what is the age of concrete? If we make it suppose 14, that means after 14 days the structure is lifted to the site from the ground level, or otherwise if it's on-site construction, when we are removing shuttering, that is the actual age of concrete. So I entered as 14 days, add, it is added, boundary condition, this is support and links, these are the original support, add. These two are added, and loading condition, self-weight we are activating at the first day of the first construction stage, add, apply. The first stage is defined, and now the name is stage 2. For the same duration, structure, the element is activated already, boundary is already assigned, a load is self-weight is assigned, the remaining load we have to assign one by one. Now if in case if you are applying the pre-stressing, now you can see for the pre-stress activation, generally we will be having first and last day of load activation in the loading data. And in between, if you want to activate any of the load, then that duration we have to mention over here. That is called additional step. Suppose it's a 14 days you are giving pre-stress, the post-tensioning. That is after 14 days in the second construction stage. We are defining second construction stage. So this 14 days will appear here. So select the pre-stress at the 14 days, add. Again for the wearing surface, at the last day, add. Again for cross barrier, at the last day, add. So this is the condition, apply. So stage 2 is defined. Next is stage 3 for long-term creep and shrinkage function. So we are giving the number of duration is 10,000 days. And click OK. So what we are seeing is we have defined the 3 construction stages. And first one we are activating the member and the self-weight. Second we are activating the pre-stress, cross barrier, wearing surface, load. And then the third stage for long-term effect. So we are giving 10,000 days. Now the construction stage is completed. And go to analysis, perform analysis. So the program will take little more time than the normal analysis, because for every construction stages the program has to calculate the result and store internally, as well as for the moving load analysis it is running through the influence line diagram method, so that we can directly get the maximum position and minimum position. In between, if you want to influence any parameters, then we have to do it manually. Okay, so analysis is completed. Now go to the result part. The first one is load combination. Go to load combination, concrete design, auto generation, select the code as the concrete, and select the standard as the 6 load combination. We having as 6 LSC, that's the limit state design, and click OK. So these are the combinations for serviceability and strength condition. And if you want to activate, if you want to make any load combinations, You can do it manually also. This is for your combination. And for the envelope case, if you want to make envelope load case, go to the general auto generation, concrete. This will give the envelope load case, envelope load combination. Fine, this is the load combination which we have defined. Now we will see the result one by one. Go to the reaction port. These are the individual load cases and load combination. We can select any load combination and check the result for the combination, value and legend. So this is showing that reaction forces. And then deformations for the same load combination. You check the deformation contour. This is the displacement contour values. And next is the forces beam diagram. My is the bending moment. This is the bending moment for this load combination. Fz is the shear force and mx is the torsion. So this is the forces, and next is the stress value. Let's go to the stresses, beam stresses. This is the beam stress diagram with a deformed position. We can see the structure behavior also. So this is the stress location. Now as we saw the result in the form of color contours, now we can see how to see the result in the form of tables. So the result, last column is the result table. Go to the reaction again. Select the load cases. We can see the reaction forces in the form of tables. Again for forces, beam forces, select the individual load case or any load combination, click OK. So this is the force table, which is having that your axial force and shear force and torsion as well as the moment. And then you can check the result for stresses. This result table which gives your axial stress, shear stress, bending stress, and y direction as well as z direction. And this is the combined stress, CB1, CB2, CB3, CB4. And these results we can save in the form of report table. Right click, dynamic report table. Even in the color control for model file also, we can save it in result picture. So this is the report file we generated. Now we did the precessing part. So how to see the precess loss calculation? Let's go to the resultant table, go to tendon loss. Now this is the T1 is the cable number, the T1. This is our stage. So we have activated the cable in the second stage, so that's why we are getting the result from second stage onwards. So this column which is showing your stress remaining in the member after friction and slip, this elastic deformation loss, creep and shrinkage loss, relocation loss. So this is the loss which we can get it in the form of tables, and you can change the table, the cable name. So automatically the result will vary according to the stage. So in this way we can see the precise loss calculation for every cable in every construction stages. And this results also you can export to Excel sheet. There's an option you can export to Excel sheet. Fine. So now after that, we have done the modeling analysis is completed. We have done the load combination also. And now what we have to do, we have to do the design part. I'll show the design feature. Go to the PSC part and parameter, it is as per IRC 112. So this is the parameter, and input parameter, design parameter for ultimate limit stage, moment resistance, and processing steel type is a smooth bar and wires. We can select best strands because we are using the strands actually. And then the output parameter, we can check for ultimate stress. I'm selecting all the conditions to check for the design criteria. And click OK. And first we have to define the material type. This is the material what we have defined, that is the embodied grade of concrete. Along with that, I have to define what is the steel grade also. It is FE main bar is FE 500, sub bar is FE 415. Modify, it's added. Next is design position. I can select any one position, that is this blue one, center position. Apply. For output position, for same member I'm selecting. For positive moment, negative moment, shear resistance and torsional resistance. For ith and jth, two end of the member, we are checking the results. And then serviceability load combinations. So this combination we have to select it accordingly. Let me see the combinations. Let's see this. So first four combinations I made it for serviceability, remaining for strength condition. Now we can see the combination list. For the cost permanent, frequent and characteristic combinations, click OK. And next is the short-term and long-term effect on the structure. This will identify automatically from the pre-stress, primary and secondary forces, and other load parameters. And then exposure classes. I have to select your top is severe, very severe, and bottom is moderate. And apply. So this design part is applied. Now do the perform design part. So it's doing the design. It takes a little time. Let's see. So in generally the design output is in the form of Excel sheet. We can see what is the formula, what is the code number, class number, the stress diagram. So all the parameters we can see in the design report except that Excel formulas. In the meantime, if you have any questions, you can ask. This will take a little more time then. Yeah. If you have any questions, you can ask.
Sir, this defining this rigid links.
Yes.
So suppose if you are doing a continuous bridge, I mean discontinuous bridge over the pier.
Okay.
Reaction are both horizontally and vertically eccentric from the pier center.
Okay.
Pier cap.
Right. Right.
So how do we define the rigid link there?
Right. So actually, when you are making your rigid link structure,
Just
if
explain,
it
sir.
is,
That's
yeah, right.
okay.
Explain it in the drawing part.
Okay, okay.
If suppose this is your pier and your cross section, I mean, your pier cap is like this,
Uh,
okay, and for example, it is like this, okay, and your one structure is going on like this, another structure is going like this. This structure is having a bearing at this location. So what we have to do, we have to make one connection over here. Suppose two bearings are here,
okay.
two bearings are here. And instead of making your model with line element, instead of making the line element, this you can make as a plate element. And mesh it. So once you're doing now, if you do the meshing part, automatically this member will get divided and we have the node at every point. So accordingly, you will get a node at this location to connect over there. So in that case, we can directly make this is the plate element, this is the beam element. So we can make the element types are the pier cap is plate element, others are beam elements.
Okay. And
Just tell me.
um, that's
That is possible that cross section you can bring it from AutoCAD. That is from there's another interface that is called section property calculator. Section property
uh,
calculator. So if you
okay.
click here, this will show the another interface over here. Here you can bring your AutoCAD section.
Okay.
This is the another window will
Uh,
open. Here you can import from AutoCAD.
okay.
Fine. Now the design is completed. I will show the design output. Excel report. So this report is full, complete, detailed one. We can directly print it. Is kind of printable format. Now you can see this is the printable format. So fine. This is the our other loading part for the simply supported two-cell box girder, including design features.
Hello, sir.
Yes. So thank you very much for joining this webinar. I will see you in the
Please
next webinar. Thank you
send
very much.
videos on this one, video on this PDF, sir.
Like,
PDF? Fine, fine.
Then
Yeah, yeah,
like to
yeah.
send earlier session, same.
Okay, 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 fine. We have some record. Yeah, we have some recorded webinar, recorded. Sorry, the PDF file tutorial. I'll send you for the references.
video.